glad to be here. So this is kind of, as you will see, this is kind of a personal views, largely supported by data, but some from incomplete and anecdotal sources through consulting, teaching, interacting with people. Perhaps biased to some extent, hope not too much, and something I would not have done earlier in my career. There are some things that are very sensitive politically, so you don't want to say those, but now I think I can. So this is what it is. I haven't done this before. I use some of this in my teaching. I'm teaching different classes. One is in microbial, general biotechnology, biochemical engineering. One is in biomanufacturing for therapeutics. I have actually a lab that does both kinds of things. So I have sort of in some ways a more comprehensive, I guess, perspective from that point of view. So what is a fuel molecule? I always ask that question the first day in biochemical engineering class, and the students says, tell me a fuel molecule. They will give me examples. They will say hydrocarbon, okay, it's a coal. If you want to define a fuel molecule, what is a fuel molecule? What does it do? What does a fuel do? I mean, for humans, I mean, human core society, right? I'm not talking about nuclear fuels here. Basically, it's a dense packaging of electrons, right? That's what it is. Nobody can give me that thing, and then when I tell them, says, yeah, I didn't think about it this way. To donate them to oxygen for combustion, to give away combustion energy, the more reduced the molecular moiety, the better. More dense, hydrocarbons, coal, and so on. Now, biofuel, what is a biofuel, right? So what we want to do is how electron dense can be sustainably biologically produced molecules. What can we do with that, right? I mean, obviously, you know one of them, which is ethanol. We'll revisit that. But what is biologically sort of if you wish, the original material? You're talking about sugars, either as monomers or as polymers. Sort of like think of cellulose, you think of polysaccharides, you think of starch, and so on. So that's really what we're talking about. And at the end, you have to convert this to something that is practically usable. You cannot put, say, sugar in your car engine, right? Try that. You want to do it, you see you're not going to get anything out. You cannot really do that. So we need at the end good source of renewable electrons. And where do the electrons on Earth come from? That's another question I ask them. They always say, but they're here, right? Are they? Where do the electrons on Earth come from? We ultimately come from the sun, right? Okay, so it's nuclear reaction, fusion. It's the fusion reactions in the sun that feeds the Earth, right? So we depend on nuclear energy. We don't like the concept, you don't want to say it, but this is really what it is. So let's do a little diversion here. How long would life on Earth sustain if the sun disappears instantly? Suppose now the sun goes off. How long are we going to be alive?
Have to be the time constant of the temperature going down.
So give me
Probably weeks.
Give me weeks, days, months,
years. Minutes, 20 seconds around.
All right. So that's ChatGPT, but you have to check it. And it's actually pretty clever.
Oh, yeah.
You have to push it. 1 week, average temperature drops by 15 degrees centigrade to below freezing. Plants that depend on sunlight biosynthesis die. So in 1 week, there will be no more plants left. We'll all be dying, right? That's what we get. In 1 year, the average temperature will be minus 37. So it means everything is frozen, including the oceans, right? What is left then is the deep sea hydrothermal vents powered by the internal energy in the Earth, right? They survive longer, but there will be no life on the surface. So basically, we depend on the energy we get from the sun. So this is the idea of the renewable stuff. It's really the electrons we get from the sun, and we can take it, say, from biological sources to be able to convert it to something. So that's really the essence of the biofuel we're talking about. Don't get too anxious about it. Some will eventually burn out, but slowly. And by then, humans will have destroyed life on Earth in any case. So we're not going to worry about it. You're going to find we just don't need more than 120 years, maybe something like a couple of your generation will live longer than that. So we need renewable electrons for renewable fuel molecules. That's the essence of that. So let's look now what chemicals have been produced traditionally biologically. Ethanol has been produced in small scale since at least the prehistoric times. We knew that Egyptians were producing some kind of beer even in 4000 BC. Then the acid of butanol fermentation, which is an interesting, this is one of the areas to start in my career, still care about it for a variety of reasons. It's something you can teach in political history because the explosives, the wars, the main inventor became eventually the first president of Israel, and so on. So that's an interesting lecture by itself. Citric acid has been produced for years, still is produced by biological means. An antibiotic starting about 1940. That really is the field that gave rise to biochemical engineering. That's the deep scale fermentation they didn't know whether they would be able to do. And the American government, the British government said that we have to do it because at the end of the war, we'll have millions of wounded people who will die from the infections of the wounds. And they were able to scale it during the war, but they wouldn't be able to publish how. And then indeed, we did have penicillin in about 1945 in large quantities to treat millions of soldiers as well as civilians in Europe and the United States. Specialty chemicals, natural products and drugs, several of those, commodity chemicals, even amino acids. Amino acids until about 20 years ago was a specialty chemical. Now it's a commodity chemical. It's produced in enormous quantities here, and that's an art we've mastered very well biologically. And organic chemistry that don't even come close to producing amino acids with that efficiency. Then food and protein for humans and animals, that really is a growing area again. And protein and whole cell therapeutics, this really is the $108 billion industry. So which of those is economic? Ethanol production for as a biofuel or as a chemical, that's a conditional sort of statement to say whether this is economic, but we do it. Now we'll revisit that. The acid of butanol fermentation, it is not economically done in the United States or in Europe, but in China, they've mastered the art and they do it because they don't have too many other resources. So that's being practiced at least in some countries. Citric acid is fine. We do this very well. Of course, antibiotics and semi-synthetic hormones, including steroids, we do those. Specialty chemicals and natural products, we do that. Commodity chemicals, all of those really are possible, but biofuels other than ethanol, that's debatable, actually none of that. And then food and proteins, we're back now to the field of single cell protein, basically producing protein from microbial cultures, very effective. Some of them are already in the sort of things you buy in the grocery store. And if you want more details, I'd be happy to tell you that. But really the big thing, the one that the industry that hires 80% of our PhDs and bachelor students in the biotechnology area is the protein therapeutics. This is a $108 billion industry, which is growing very fast. So this is the big gorilla in the room. And surprisingly, that field has very little support by the federal government, and we teach very little of that. So the industry complains we don't have enough people trained to be able to work in the field, and that's the one that grows by about 10% every year. And in fact, it is likely that it will accelerate for a variety of reasons. So I will leave that aside. It's an interesting possibility, but we need now to look from a different point of view, what kind of process are we dealing with? Classification based on biological ensemble. Enzymatic, there will be a single reaction. We have several. In fact, the conversion of one type of sugar from corn to another type of sugar, the stuff you hear about the president, he doesn't like the Coca-Cola with this sugar, he likes it with the other sugar. This is done enzymatically. Purified or crude enzyme preparations, immobilized enzymes or free solution, enzymes in the whole, in the dot cell. This is how we actually do the conversion of the sugars from the corn. Whole cell, basically the large scale fermentation, like the ethanol fermentation. This is done in enormous quantities of cultures. The scale of those is 150,000 gallon fermentation. It really is very large scale. Selected, we use basically evolved strains that we've trained them. All of the strains that produce ethanol come from prehistoric strains that have evolved. So some of them actually are toxic to humans. Those that we use to make bread is the same origin as the one we make wine, we make beer, and so on, but they have been bred to deal differently, and they will make us sick if we use them to drink alcohol from these kinds of strains. But nevertheless, this is done well. Then we have now engineered strains. So we have really sort of like several of them. I will explain a little bit about the PDO, the BDO, the succinic acid, and artemisinic acid shortly. And then we have now hybrid technologies where we combine biology with chemistry or catalysis and vice versa. And there's now a new center that Professor Pistikopoulos and I work, several others here, the BRC, the University of Washington, Washington University in St. Louis, which uses electrocatalysis to produce small molecules, and we take the small molecules biologically to produce more valuable molecules in the second step, and you can actually reverse the process. You can start with biology and then use, catalysis to do something else, and we'll revisit this a little bit again at the end. So the cost and the viability of the bio-based chemical depends on the substrate cost: sourcing, flexibility, availability, purity, product yield, complete utilization, fermentation cost, mixing, aeration, gases, energy cost, batch fed, batch continuous, duration, strictly sterile or not, and so on. And of course, at the end, the most significant cost in manufacturing chemical is the separation, the purification, and that depends on all of the above. For example, say, if we could produce ethanol 40% volume, the cost of producing ethanol versus where we stop now at about 14% will be reduced by about 60 to 70%, which will make it very economical. But we cannot produce ethanol at such high titers because the cell is dead. So that really is an issue. Same thing applies to any kind of chemical. It's really the toxicity of the chemical that prevents the higher titers, the higher concentration that really is essential to be able to devise inexpensive separation and purification costs. At the end, all of the success of the biological products rely on this, and this rely on that. So you have really sort of like a connection between what is the substrate, what is the organism, what is the tolerance, what is the yield, what's the selectivity, how this will affect the separation purification cost. So that really is the crucial element. Let me focus now on for simplicity on processes using whole active cells. I assume that single enzyme processes and in vitro multi-enzyme processes are specialty cases for low volume specialty chemicals. There's a silliness in the argument that both academics and the federal government, because they do not really know any better, they listen to some academics that say, oh, we can use in vitro biosynthesis to produce commodity chemicals and fuels. Doesn't make any logical sense. You can try as much as you want to sort of do a TEA on this. You will see that it will be dead on arrival. So I will skip on that. Classify then based on the product value. Expensive products of high added value, or the organic chemistry synthesis much more expensive. That would be the case of all the antibiotics, several of the vitamins. For example, vitamin B12, they were able to use an organic chemistry synthesis feed about 30 years ago. It's a very complex molecule, but biologically you can produce it by less than 1/10% of what it will cost to produce it by organic chemical synthesis. Antibiotics are artemisinin, taxols, opioids, steroids, vitamins. So these are the kind of molecules we're talking about. The cost of the substrate for these guys is not really a major contributor. It's just irrelevant. Same thing applies with manufacturing or product therapeutics. The cost of substrate is not a big deal. Everything else is, but not that. Higher value commodity chemicals, amino acids, succinate, lactate, PDO, BDO, there I think the cost of substrate is important, but it's not really critical. It's not going to break the process from that point of view, but it is important. Finally, you have now the subcommodity and the biofuels, which really is the most important element. The most important cost is the cost of the substrate. And by that, I mean, I don't merely say the actual value per unit mass, but also availability. Where is it, how concentrated, what are the sources, whether it can be done in a distributed way or in a centralized way. That's important. So with that, I'll do 3 examples here. One of it, so we'll start with artemisinin. Most of you perhaps have heard the name. It's an interesting story. It's really a grand success of metabolic engineering for synthetic biology, but unfortunately it failed. I'll tell you why. then isobutanol as a fuel or fuel precursor, and then the 1,4-butanediol, which really is a xenobiotic. That molecule does not exist in nature, is man-made. And that's the one that shows that we can really do things if the synthetic biology and the metabolic engineering and the process development are done right. And that really is a success story from that point of view. So we're looking at here malaria. It's the Plasmodium parasitic infection via the Anopheles mosquitoes targeting the red cells. Basically, the people that are infected with that, they will die because they cannot really provide oxygen for that. So that's really what happens is when the parasite really affects the red cells, it affects everything here. You can see that these people really suffering. There's a lot of it both in Asia, but especially in Africa from that point of view. The World Health Organization and the Global Fund recommended switching the artemisinin-based combination therapy in 2004. This is the molecule. This is the artemisinin, which really inhibits the parasite. And this actually was known. It was produced by the Chinese wormwood plant, the Artemisia annua. And Professor Yu too got the Nobel Prize a few years back for that. But at the time, it was very difficult to get enough of this material, and the supply was extremely limited. It wasn't enough to be able to treat even 10% of the population that needed that in Asia as well as in Africa. So here comes then the Jay Kisling's work, the engineering the mevalonate pathway by synthesis. You start with very simple sugars, you get to acetyl-CoA. At the end, through ergosterol, we will take several other steps here to produce the artemisinic acid. And then with that, you use a simple chemical step to convert this here into artemisinin. So the paper was published in Nature in 2006, eventually taken over by development by his startup company Aberis in the San Francisco area. Gates Foundation gave a mega grant to them so they can develop it and make the material available in Africa and in Asia. Brought to market under the One World sort of Gates Foundation if you wish, mentorship, auspices by Sanofi Aventis, who really took it over in terms of manufacturing, fermentation in Bulgaria, and chemical finishing in Garesio, Italy. To do that, launched in 2013, produced a lot of material from this, and really provided basically 1/3 of the global need. It's easy to scale up. Once you have the fermentation that can produce 10 times as much, it will do it. But things did not work well in the marketplace. Aberis, in collaboration with this, as I said, produced the material, but the Chinese developed better technology to extract it from the plants. They really were able to produce so much artemisinin, and the cost was 1/4 approximately what was the fermentation cost. So basically, with all the success, with all the metabolic engineering, with all the synthetic biology, fermentation process was not competitive. Sanofi abandoned it, transferred it to the non-profit medicine malaria prevention, that in case there is a year they cannot produce enough of the plant, they can still have it as a standby to be able to use by fermentation. A glory of synthetic biology, but it failed in the marketplace despite the very high cost. However, this is subsidized. This is not something that people who use malaria can afford to buy the material, even at the low prices the Chinese offer. So this is kind of complex. It was never sort of meant to be able to treat people in North America and Europe. It was never approved to treat people in North America and Europe. But it is to just tell you what is it that we can do biologically. Now I'm putting the isobutanol story, the Butamax versus Chiba. In 2005, DuPont, Butamax, it's a venture between DuPont, the old DuPont, and British Petroleum, filed a provisional patent to produce isobutanol from glucose using E. coli or yeast as host. It was based on the enhanced what we call the early pathway that the alpha keto acid biosynthesis known since the 1950s. A new genes better expression plus some genes deletions to be able to enhance the flux. Jim Liao's group at UCLA published in 2008 a paper in Nature describing the execution of this isobutanol pathway in E. coli. GIBO then was formed and licensed the UCLA patent and moved the pathway to the yeast. And GIBO produced for a short while at least isobutanol alongside with ethanol in a plant in Minnesota. Not clear what they needed to produce ethanol. They don't produce now the isobutanol, they just produce ethanol such that the company can survive for a little bit longer. And it was meant to use it for sustainable aviation fuel production. Basically, you take ethanol, then you dehydrate it through some sort of means with or without hydrogen, and then you produce the sustainable fuel, which really is the only avenue we have now to produce SAF, and I will revisit that shortly. So a minor contributor to the biofuel cost, volume, and profit margins, if any, are not there yet to deal with that. So it's been glorified. Everybody wanted to do Ethanol, metabolic engineering, this and this and that. But that's the history behind that. This is the early pathway that we have been teaching in biochemistry for several years. It can be manipulated. You cut off a few things. For example, you need to cut the lower part here, such that once you reach the alpha ketoacetic acid, it will go to isobutanol as opposed to going to the lower part of the early pathway. So in the footsteps of the celebrated DuPont Zenencor PDO, this is the 1,3-propanediol in 2000. Genomatica developed this process, the 1,4-butanediol process here from scratch. So this is a molecule that doesn't exist on Earth. This is a xenobiotic, but it's a phenomenal monomer to do polymer synthesis, much better than most of anything else. For example, compared to the natural 1,3-butanediol, the 1,4 is much more superior chemical for polymer synthesis. It's proven successful in E. coli based on metabolic engineering project. It's a novel chemical. It was commercialized by licensing Department of Chemicals. The most recent one is the Cargill. Cargill will build the facility to be able to produce the 1,4-butanediol, although some think that the profit margins will be marginal. But Cargill is a private held company. It's the largest family-owned company in the United States, perhaps the world. They can do business, and we don't understand what is the profit or the business model. Use a lot of ethanol as well without having any sense of profits. But if you look at it from the integrated point of view, they just utilize everything they can possibly get out of the corn to be able to do things. And I think this is part of the portfolio. So I count this as one of the successes of metabolic engineering, the 1,4-butanediol, but that is to produce a monomer, to produce a chemical rather than a fuel molecule. So this is the seminal paper published in Nature Chemical Biology. Involved several people, including former student Sang-Yep Lee in Korea. This is the pathway through which they did it very clever. Something that doesn't exist in nature, but they combined known enzymes and so on. This is something actually we could have done ab initio computationally, and of course with AI now, it can take about playing for about 15 minutes to tell you this is how you're going to synthesize the material. Great example of industrial process based on metabolic engineering, synthetic biology. One wants to use the more attractive parallels here and produces biotic. Now, let's revisit now what is the famous list of the Department of Energy of chemicals for renewables. So there was one list in 2004. You can see the chemicals here. Then there was a new list here in 2010. Some of them have been eliminated. After trying all of this, they expected the Bioenergy Centers that started in 2006, by the end of the 50th year of them, the half of the first period of Bioenergy Centers would have produced all of them, and they were saying we don't want ethanol. Then in 2010 realized that we're not able to do any of those. So they said, okay, ethanol is okay, so they put it back in the list. So they have those now. You recognize some of them. Actually, we've done, there were already several of them done. For example, lactic acid and succinic acid we've done practically before the Bioenergy Centers really started operating. So this is what it is. Ethanol, glycerol derivatives, this all fermentations. We do not know who exactly practices. We know this practice in China and Asia. Lactic acid, actually, Cargill produces lactic acid, succinic acid, several companies do this. The rest of them isn't quite sure who is practicing, but then everybody's trying to do this. Professor Aristide has a group trying to make the hydroxypropionic acid strain development more effective to be able to do that. But there's several others that are not on the DOE list, which are really important. This will produce all those chemicals. For example, the 2,4-butanediol was never on the DOE list because DOE didn't even know that this molecule could exist. So you can see the federal government follows science, but it doesn't follow it very well. It is being influenced by 2 or 3 or 4 or 5 or 10 academics who tells them we need to do this, we need to do that. They don't have the ability to independently make judgments as to what is relevant and what is not relevant. So we have been producing amino acids, antibiotics, polyhydroxyalkanoates, not in the United States, but in Korea and in Japan. These are very important molecules. They failed in the United States in the marketplace, but then Korea and Japan have different priorities. They want to have renewable material. For everything we do consumers, they want to have everything, something that can be degraded. So then it's important to be able to practice that, and they do. Some butanols, not in the United States, PDO, 2,4-butanol, as well as the 2,3-butanol, not in the United States, but in China, and then human and animal products. So this is basically what the government Department of Energy tells us. This is really what is being done, and hardly the two things really coincide in any way, because the succinic acid and the lactic acid were started way ahead of the Bioenergy Centers, way ahead of the first DOE list. So back to ethanol here, the volumes and the profitability. So I asked ChatGPT several questions, and I summarized what I got out of it. You can use it, but you should be able to interrogate the answers you get. The individual pieces where they say, well, I'm not sure about this, how about that? You ask an additional question, then you get the bottom line. The bottom line is this: no ethanol producer today operates fully, subsidy-free, profitably under standard market conditions. That's the reality. The ones that come close is Brazil and India. And why is that?
Cost of labor is cheap.
So what do they use in Brazil and India as a substitute? Okay, we use corn, right? In Europe, they use potatoes, right? Or various kinds of grains. So why is it that the sugar is less expensive than the corn sugar is? We get 3 crops a year.
Yeah.
We get 1. Yeah. So that really is the big thing, that they are there. And in any case, for more than 40 years now in Brazil, all of the fuel comes from ethanol. In fact, they really changed the engines of the car so they can use pure ethanol to be able to get the cars moving. We don't have that will, and I don't think it would be acceptable to the American society or European societies to be able to do that. So some pockets of profitability, especially during high variable price cycles. They remain sensitive to the input costs and relying government mechanisms. They're so brightly done. What ChatGPT knows how to read the enormous literature very quickly. It will slow you down a bit because it's looking for that. But technological advances, collocation strategies like waste heat utilization can significantly boost the margins, but they're not complete offset to broader systemic costs. Unless the oil price goes over $200 barrel, it's not going to be sustainable. And that, I think, really puts every other molecule at disadvantage until we get to that point. And now, with electrification of the cars, it is unlikely that the cost of oil will ever reach even $100 barrel to be able to think there will be an area where we can do that. Nevertheless, I think this is an area where process technology as well as biological engineering can really improve the production of ethanol and make it cost effective. Yet DOE didn't want to hear a word about it. And now it's very difficult now to convince investigators to pay attention to this, where they can do better, and I think it can do better. So we do not really have any new biofuel molecule after all, and not like to get one in the foreseeable future. So some historical context here. So the DuPont butanol announcement in 2006 led to 3 significant outcomes. First one, a frenzy of interest among world war governments, venture capitalists, academics, the public biofuel became part of the common language. Ask anybody in 2000, say, what does biofuel mean to you? They say, what does it mean? Now everybody in high schools, elementary schools, they know biofuel, they hear it, from the media, they hear it, from newspapers and so on. And US DOE started the Bioenergy Research Centers. There are 4 of them now. still going after almost 20 years, and they haven't produced a single molecule that can reach really the marketplace. Yes, and it's unlikely that they will, assuming that they can still operate longer than that. Enormous R&D investments, hundreds of startups, but what do we have to solve for all of that? No biofuel molecules or processes, not even a new process to produce commodity chemicals. Not a single molecule made it after all these investments. So what happened to all of this money here? A lot of small and large investors, this has lost a lot of money. Some made a lot of money the usual way, which means to say, you go and have an IPO, you convince the investors, you go an IPO, you sell your shares before the company goes bust, and you make money. That's actually both VCs and clever academics make money, but then they take the other investors for the laundry, right? Okay. We have done some extraordinary sciences. This really is indeed a major gain. Useless, but interesting. Published a lot of glorious papers in high-end journals. Academics count their worth, but how many papers they published in Science, Nature, and Cell Press. That's how they value their worth. This is the dollar currency for academics. Whether you like it or not, they all dream about doing that. Partnership crime. This journals really publish this stuff. A single paper in Nature can really help you raise a lot of money through venture capital, because they say if it's published in Nature, it's got to be very important so that we can use it and we can invest money in that. A lot of chemists of synthetic biology and tiny little titles we always get a proof of concept. Everybody says this is a proof of concept, we need optimization. That's the story we have been hearing for the last 25 years. A lot of proof of concept, no optimization, no reality. But we all knew that none of all of this would ever make any translational sense because it was lacking rationality. This could not be really scaled up, cannot be optimized even to do it. A simple example, amyris and the farnesene. So there was this molecule here. Like me, I heard the name and said, it got to be a hydrocarbon, right? So it is a trans-beta farnesene. Scaffold of specific chemicals, synthesis from sugars, symbiofeed. When the paper was published, everybody said, what a glorious thing synthetic biology can do for us. They used it to do DES and LCAs and all of this, convinced the investors, convinced actually a family from Brazil to invest enormous quantities into this molecule. So the maximum theoretical yield for farnesene, this is the molecule, C15, is 0.25 grams per gram of glucose. The actual yield is less than 0.15. So you produce very low, reduced material from a lot of sugars. So for every mole of farnesene, 9 moles of sugars must be utilized under ideal conditions. You produce a lot of CO2 to be able to do it. Basically, sugars contain oxygen, and with hydrocarbon, you have to remove basically all of the oxygen, so you need to enrich it in electrons. So the way to do it, you throw away a lot of CO2. Does this make sense for sustainability? It doesn't. So practically use less than that makes no economic sustainability sense, even as a specialty chemical. So hard to calculate. I asked again ChatGPT, and I had to do a little bit more. So between $1 and $10 billion was spent by amyris process development. And after about 15 years, amyris went bust because none of this made any sense. We knew it from day 1, or maybe day 5, or year 5. But investors didn't understand the math, or they didn't have common sense because nobody understands, has the integral sort of ability, somebody who has been in the field to say this doesn't make any sense. Why do you want to produce hydrocarbon by wanting? Makes no sense. By the way, farnesene, it's an interesting molecule. We actually eat it. This is part of the green apple flavor. So plants produce hydrocarbons, right? Do humans produce hydrocarbons? Do we have production of hydrocarbons in our body? We do. We produce hydrocarbons in order to be able to produce glycosylated proteins, and all of our proteins, or 99% of them are glycosylated, so it requires to start with a hydrocarbon sort of skeleton, the scaffold to carry molecules to proteins to be able to do it. So this was a natural product actually in many ways. So that's done. No fuel molecule then, biofuel was a chimera, but wait a minute, there is biodiesel, right? That's not a fermentation product. It increases by about 7 to 8% a year in production, mostly in Europe and in Malaysia, in Asia, and so on. It still constitutes 33 to 4% of the total diesel consumption. It's increasing, but it's a small dent with the energy production for biological means, and that simply is a natural extraction. You take seeds and you convert them into biodiesel. Then sustainable aviation fuel. Well, what is the benefit of it other than consumer sentiment? The whole point of SAF is to tell airlines to tell you, don't feel guilty for the tons of CO2 we have to throw away for you to fly, because it's sustainable. Sustainable in what sense? You have to throw the CO2 away to be able to condense something that you can get from sustainable resources, so you can put it presumably in the airplane to be able to. It's a complex issue. People want it, airlines want it, but what is the price? How much CO2 must be produced to do that? Let's do a case study again. Thank you again, ChatGPT. I knew the numbers, but I wanted to make sure that they will confirm them. So this is now the ideal stoichiometry. 37 moles of butanol, of sugar, glucose in this case, to be able to produce a C12. So this is reasonable representation of the jet fuel, the C12, right? So you can see, you produce a lot of CO2 to be able to do that. This is the ideal chemistry. Basically, you take glucose to ethanol, ethanol dehydration. You can, if you have hydrogen, cheap hydrogen, and nobody has cheap hydrogen yet, and the stoichiometry is a little bit better, but not really much better. So again, it's sort of like, what do people want to make them feel better? What airlines want to make them feel better? To be able to sort of foster all this kind of stuff. And there's an industry trying to produce SAF to do that. So, okay, new large volume biofuels makes no sense. We got the geological endowment of fossil fuels that took millennia to build, and that's really what we're sort of using now in the foreseeable future. Maybe nuclear energy at the end, maybe it's the way to do it. It can be practiced, it's expensive. You cannot charge the full price of the cost of the nuclear energy, especially the disposable the material. But at some point, humans have to make do with whatever sort of risks need to be taken to be able to satisfy their needs. So let's examine then the production of chemicals renewably. We talked about it. You use those already done. Pick your fight in your product and think out of the box. I gave you the list of what we produce, what is possible now. Then I think your generation, the new generation, need to be thinking something out of the box in small steps to say, I'm going to produce sort of a specialty chemical. I'll give you a very simple example. There's a company I have worked with. They say, can I produce all of the material for diapers for babies or for all the adults renewably, such that this material will be biodegradable? The answer is you can, but the cost is relatively high, but that I think is an important target. The reason for that has to do with sustainability, consumer acceptance or desire. A lot of parents will spend a lot of money for their babies knowing that they're really dealing with material that's not producing enormous quantities of waste, especially in the third world, the diapers that the Western world produces sends to Africa and Asia. It's a major environmental pollution problem. And we don't care as long as we sell. And they're happy to buy the stuff and use it and throw it away. But the way they throw it away, they cannot even control it. Not that we control this much better in the United States or in the Western Europe, but better than they do in Africa and some parts of Asia. So that really is an important target if you're thinking creatively as an entrepreneur. But there is a disconnect between what is the real market opportunity and what excites academics, but also VCs, some industry, and federal agencies. Commodity chemicals and pure molecules are not likely to succeed as fermentation products for several reasons we discussed. Yet this has been the literature oppression in the last 37 years. They're great, but not obvious opportunities in consumer products. They have profound benefits in the food, health, and environmental sustainability. Fillers, thickeners in cosmetic, low and high-end products, especially in the cosmetic industry, we'd rather have every single ingredient naturally derived because they can claim that. And the consumer is willing to pay 20% premium. It says, I want to use a cream for my face, which all comes from natural product. That I think is a great opportunity that people need to focus more on saying, this is what I'm trying to do because I can sell at the premium, the same chemical I can produce petrochemically. If I do it biologically, I will have a 30% premium. I will say this is biologically produced. So there are several efforts along those lines, but you have to be clever and know how you're going to focus on that. Water absorbance in diapers, I discussed this in another consumer product. That I think is a great area of growth. Animal and aquaculture feed, as well as human feed, food ingredients, that's also a growing field. A lot of these companies here, if they have fermentation, they don't make in biological sense. They convert this to protein production. The company I started in 2008, which I sold my portion in 2014. They know how to do anaerobic fermentation of Clostridium organism. They picked one that was a grass, which is safe. They produce a lot of protein for this, but this organism produces also a lot of butyric acid. So now they can also sell the butyric acid at 1/4 of the price that can be produced by any other process. So basically they combine the protein that you will be eating in your high protein bars that you buy. It's already in Europe. They're manufacturing in the Netherlands. They're building a plant in the United States. And then this is a case that you can say, yes, we can produce commodity chemicals as long as we have it's a byproduct rather than the main product for the fermentation. And actually, butyric acid makes a lot of sense. You use it to do SAF. You still insist on SAF. Because if you think butyric acid has a long hydrocarbon chain, and then it has and then they have the two oxygen molecules. That really is much more cost effective in doing the condensation to produce the hydrocarbon from butyrate. You have 3 molecules you put together, you get a C12 to do that. Chemically or rheologically modified biopolymers, components, especially the environmental detoxification devices. These, I think, are all the areas that we need to focus instead and sort of accept the fact that biofuels, the way we understand it now, with the common language, and that may change in the next 20, 30 years, is what it is. These are the challenges. So we have largely mastered the chemistry of biological pathways, both computationally using rules of chemistry. And that advance actually was done about 25 years ago. I'll be happy to sort of, I teach this material in a good quality with my Hatzimanakadis, were really the ones that developed that. We have the ever-expanding database of actual genes coding for enzymes catalyzing desirable reactions. So we can design any feasible pathway and test it both in vitro and in vivo very quickly. It can frequently make cells produce small amounts of desirable metabolite. Small amounts doesn't make a process. That really is the key. So we have good platform organisms. In terms of synthetic biology now, with AI coming into this and organizing all of this sort of material, I think we can do miracles. So this has really accelerated the process, but as design, this is chemistry to start making process. In the absence of process data, AI is totally useless. In the absence of any data, anything you want to have without data is useless. AI doesn't understand to do synthesis unless there's data to do synthesis. If you have chemical rules, say protein folding, the Nobel Prize recently, you have rules, you have really specific amino acids that allow you to do chemistry dynamics, be able to use AI to make sense out of it. Pathways, we have rules, we have really database to do it. Processes, we don't have enough data to be able to make sense out of it, and that is something people don't understand. They think that AI is magic. AI is not magic. Basically, it's organizing complex data as long as there is a pattern in the data. And that, I think, is the crux of the matter in this area. But that's not sufficient to make an industry make money. You need high yields, you need rates, you need process intensification. The lower the value of the product, the higher the yields and the rates of process intensification necessary to make a process practical, at least in the United States. In China, it's a different society, operates under different constraints that we don't really understand. We have our own constraints and perceptions, but that's the reality for the rest of the world. Process integration design can be done reasonably well and accurately, but if we have good biocatalytic properties, because we can design bioreactors even for difficult cases. A lot of people have the conception you cannot do gas fermentation. You know, when your substrate is gas, there's problems with mixing and all of this. Surely, but we've mastered that kind of art. People keep rediscovering this because we've stopped teaching it, and that is part of the problem, is that we don't teach max interfacial transport in any case. most of the undergraduates finishing bachelor's degree, you ask them about, tell me about the Sherwood number. What does it mean for you? They say, what is interfacial transport? They just don't have a clue. It's a walk out of it. And yet, every single chemical engineering process in interfacial transport process, or whenever it teaches interfacial transport, can make sense out of that. We can select and cost quite effective predictably downstream processing steps if we had to do that. What would then make success in the biocatalytic properties is the yield, how much product per gram of substrate, which affects the process economics during the high substrate cost, sustainable, if possible, stable, continuous manufacturing, high productivity grams of product per gram of biomass, high productivity volumetric, gram of product per bioreactor volume, which really tells us how fast and effectively cells can produce a particular product, so we can really intensify that. And then there is has to do with the bioreactor facility sizing. The higher the numbers there, the smaller the reactor volume, the smaller the capital cost, but also the operational cost, to determine how much process intensification, is necessary to do that. So we can do metabolic engineering. We can synthesize pretty much everything that it's possible, even xenobiotics. But we haven't figured out how to systematically and predictably engineer high and stable rates, small QP or capital QP. And such activity really brings very little glory to academics. Who wants to write a grant to NSF to say, I'm going to focus on this? But I'll be laughing. They're always looking for chemistry, looking to produce a tiny amount of this chemical, the other chemical, novel pathway, something jumping. I'm going to put a neural network in there. I'm going to do a synthetic switch. It will turn this on, turn this off. But none of that makes a process. Synthetic biology itself has produced not a single product on Earth. It's just something that is in the fantasy of academics. It's an interesting tool. Synthetic biology is a tool. It's not an industry. It's just interesting collaborators that need to fix this problem and create, universities to decide what they want to fund, what they want to undertake to do that. So we cannot get rid of the regulatory complexity of logic that underlies that. In other words, we know how to produce a pathway, but we cannot really tell from existing complex pathways in cell what is the regulation necessary to put a synthetic one and make it work to do the miracles we expect it to do that. And AI cannot really do any of this. Even before AI, we knew predictably how to calculate pathways to do pretty much anything. This is a reaction possible, and because it is based on reaction rules, AI can also do the same thing now. But back in Hatzmanikat's cohort, we're able to do that. They have the mathematical representation of the chemistry rules, we have the enzymatic capabilities, we have thermodynamic. All of those things are based on principles that AI can use because we have principles and data from the enzymes. And then you can say, I want to go from this chemical to that chemical, it will give you all possible options. And then you decide which one is that minimizes the steps, or it minimizes the effort or the energy to be able to do that. So that I think is great, but none of that still makes a process. So that I think is really important. Substrate cost versus abundance. We started here with the cost of the waste, the woody biomass, the corn stopper, which is the leftover from the corn, the high yield grasses, the normal yield grasses, and then the corn grain you see on the top. So then based on this, it comes from a report from National Academies and the NRC, the National Research Council. So then you decide on this to sort of get fine, but they forgot something here. They don't really have explicitly gases. They're not clear here where we use gas with that. And because gases have become again in sort of more popular in many ways, I will just say a couple of things about it. Gases, waste are not a substrate. So we have methane, right? We have a lot of them. It's dispersed. You cannot get it very easily. You have more in Texas, shale, and so on. You have syngas, which is something we can produce from waste material, but it's really very expensive technology, a huge size plants. You have carbon monoxide waste, and then if we can ever make production of hydrogen economically feasible, we may. So we're talking about here the carbon monoxide waste. This is the output of the steel mills. The steel mills produce enormous quantities of carbon monoxide. There's a company that just failed, Lancetech, who is the glory of the new biotechnology, was that many others that started there failed earlier than that. Then the concept of the electric fuels and the hybrid technology, where you combine electrocatalysis to be able to convert sort of gases, like for example CO2, into something else, and then something else using electric fuels. We use some of it coming, from the energy sort of resources, the electrons from electricity, and the hybrid technology that you combine the two of them. So the Lancetech process is based on what is known the Woodland pathway. This is the primordial pathway that apparently was developed when Earth had only carbon monoxide on the average. So let me just help you read this kind of thing. So we have here carbon monoxide sits here, right? Then to be able to create acetyl CoA, which is an essential unit, right? It's an acetyl which has a molecule here that activates it biologically, and then from there you can produce acetic acid. And this you can produce now ethanol if you have a few more electrons to do that. So originally this pathway apparently operated with just this, and then to be able to get this branch here to produce this activated methyl group here, this is just an activated moiety here, an organic molecule. Yes. You need to take this, you need to oxidize to CO2, then you take CO2, you convert it to formic acid, you go through this pathway, which has been preserved now in most organisms. But this molecule here, and this particular enzyme here that does the synthesis of this, combine this with that to create this. This is a primordial sort of synthesis. So this is called the acetosis that they do, and this is what Lancet and several others have used to be able to take carbon monoxide and convert this to ethanol. So that really is the trick with that. So from steel mills to ethanol, this is now the stoichiometry, the ideal stoichiometry. 6 moles of CO will produce 1 mole of ethanol, and it will release 4 moles of CO2. So Lancetech also failed at the end, despite the claim the motto was no carbon left behind. But as you can see, from 6 carbons used to produce ethanol, they were throwing away 4 carbons. So they were leaving a lot of carbon dioxide behind, but they didn't want to tell the public that. Nobody knows stoichiometry in any case, and they don't use the carbons either. They cannot do the calculations, so that's really what it is. Still, there is an opportunity. They established the technology and practiced it in China. They were building a new facility in Belgium. I think the Chinese companies will keep it for a variety of reasons. That you can, it's a market, it's a small market controlled by the producers now of carbon monoxide. The waste producers are the ones who control now this technology, and I think they will buy Lancet precisely to be able to use that technology in the steel manufacturing process. There isn't very much steel manufacturing left in this country. Be able to see that we'll be able to use them. Hybrid for larger, more complex molecules, biological, which makes sense if you use the combination of chemical and catalytic processes. This is what the current research center does. The reason is that the thermal energy is less expensive than source. Catalytic chemistry can use inexpensive thermal energy to form carbon-carbon bonds and remove the oxygen via dehydration. And it's much more efficient for producing large molecules. So that really is to think about, and it may still work. At the end, biology by process beyond ethanol production in small steps and in niche applications. That I think is critical. Focus on more expensive chemicals, focus on consumer sentiment and desire for renewable, degradable ingredients. Those really can get higher prices for you to make it possible, and it makes people both feel good and the environment also is good, and you can really make business out of it. Environmental applications related to fossil fuel technology. Now, steel manufacturing is not a fossil fuel, but a lot of fossil fuels, when they're being produced, they still produce a lot of carbon monoxide, and it's in a concentrated form. Together with CO2, maybe that there is an opportunity to be able to mitigate that environmental problem and make something out of that. So it is application related to fossil fuel, but it's not a substitute for energy production. We insist of fossil fuel energy production. And use waste outputs, as we've seen, substrate, waste removal credits from that. And with that, I will thank you. And I'll be happy to